All right, so Unit 4 here, right? Unit 4 is all about chemical changes, right? And what we're basically doing is introducing some of the types of chemical reactions that we're going to be talking about and how we can kind of represent those, what happens with them, just introductions, okay? So it is all about introduction to reactions, okay? So first of all, our introduction to reactions, right? We can always write reactions, whether it is a physical or a chemical change, using our kind of general method, right? So a physical change is all about change in properties but no change in the chemical formula. Okay? No change in the chemical formula or composition, right? Okay? Generally, right, our physical changes, we talk about phase changes, and this involves, right, oftentimes intermolecular forces. Okay? Um, our chemical changes, right? Our chemical changes, we have lots of different indicators for our chemical change. We could produce heat or light. We could have the formation of gas. Right? Or a solid. If we started from a liquid phase and we produce a solid or we produce a gas, that's an indication of a chemical change. We could have color changes, but really, all of these are just indicators for that chemical change could be occurring, right? But really, what it comes down to is making or breaking bonds. Okay? So it's making or breaking of our chemical bonds. So our representations, right? Anytime we do representations of the change, right, we have to follow the law of conservation of energy, mass, and charge. So we cannot change the numbers or amounts of elements. Okay? So with our physical changes, right, we could write something like H2O as a solid changing to H2O as a liquid, right? The solid represents, or the S here represents the solid, the L represents a liquid, and we could change it further into H2O gas, right? We are representing the physical change that is occurring, and we can represent it just kind of in our standard notation. But for us to represent those physical changes, right, we have to draw, or we have to write the states, so solid, liquid, or gas, okay? Um, for chemical changes, right, we have a few different ways, or a few different things that we need to pay attention to. But the big one is that it must be balanced. Okay? So anytime we have a reaction, right, we have to use a balanced chemical reaction. Okay? So if we don't remember how to balance chemical reactions, we're going to have to look that up, but it shouldn't be too hard. Okay? We should remember how to balance our reactions. Right? But anytime that we have a few different types of our chemical reactions. Okay, first type is just the molecular reaction. Okay, so for all three of our different types of chemical reactions, I'm going to write the same equation. Okay, so my equation that I'm going to use is going to use barium nitrate and sodium carbonate. If I have those two, compounds and I put them into a container, liquid, they're both, they ionize and then things are going to happen, right? Overall, I'm going to have two NaNO3, two sodium nitrate molecules that get produced, and barium carbonate. Okay? But when I do this, right, I'm going to realize that, hey, these two ionize, and this is going to be aqueous, right? We use AQ. Let me write it over here so that we see it, right, to indicate that this is an aqueous compound, that this is an aqueous compound, this is an aqueous compound, and then this barium carbonate is a solid, okay? So when we write it with the states, the aqueous states and the solid, we realize that our aqueous states, right, we should really kind of write them as the ions instead. So our molecular equation, right, has all of our pieces as molecules, but the complete ionic, right, we're going to break up our ions. So Ba plus 2 NO3 minus plus 2 Na plus CO3 2 minus goes to, right, we're going to have 2 Na plus and 2 NO3 minus and BaCO3. That is a solid. All of the rest of them are going to be aqueous. So I'm going to write my aqueous on here real quick. All right. So when we do this, right, we realize that all of our ions, the aqueous ions, really when they're in water, they separate. Okay, so we can write it as the barium ion and then two nitrate ions. Okay, whenever we do this, right, we would want to put our states on, and we would want to make sure that we get the correct charges on. Okay, but right, with our complete ionic, we realize, oh, my two nitrates and my two sodium ions did not change. So in the net ionic equation, I don't have to actually write those. I'm only going to write the ions that change. Okay, so Ba plus 2 aqueous plus CO3 2 minus aqueous goes to BaCO3 solid, right? We see that my barium and my carbonate ions combine to form a solid, okay? And this is a precipitation reaction, okay? So our precipitation reactions, right, we would oftentimes need to write the net ionic equation to show what's happening with the precipitation reaction, okay? And we have a few rules that we're going to start with our precipitation reactions, okay? We have 4 ions that are always going to be soluble, okay? So the 4 ions that are always going to be soluble are K plus, Na plus, NH4 plus, ammonium, and NO3 minus. These ions are always going to be soluble, okay? So they are never going to take place in the precipitation reaction if we have the net ionic equation, because they are not going to precipitate, right? They're so soluble that they are always, we're going to say that they're always soluble, we're always going to be able to have them in there. We are not going to form a precipitate, okay? And we will talk about precipitation later on this year, and we'll talk about more of our other ions and what happens with those. But to start, right, these 4 ions always are going to be soluble, okay? Easiest way to remember it, right, Na and K plus, that's in group 1. NH4 plus, that's our one cation, polyatomic cation, and then NO3 minus is stabilized, so it's going to be stable in the liquid as well, okay? Okay, so let's also then talk about particle representations real quick here, okay? We've done each of our representations with our formulas, but with our particle representations, right, we would want to represent a solid or a liquid or a gas, right? So if I wanted to draw the net ionic equation as a particle diagram, right, I could start with let me do it like this. Ba2 plus, right, a couple of Ba2 plus ions and a CO3 2 minus ion, right? If I have that, I'm going to put a couple more on here. Right? My reaction is going to form a solid down at the bottom of my beaker, right? And I'm going to label that as barium carbonate, okay? But in this solution, we also had Na and NO3, right? So I would have Na plus in there, I would have NO3 minus, and I'm going to draw a few of them. And then when I bring them over here, right, they're still going to be in the solution, right? So if I do that, right, I drew 2 of each on both sides, so I would need to draw the same number on both sides. Okay? So in this case even, right, if I realize, oh, I have 2 bariums, right, I would need to draw 4 sodiums and 4 nitrates rather than just the 2 that I drew, right? And that's starting to get us into our stoichiometry, okay? So we'll come back to that in a second.